Hello and welcome to Limitations of Physical Measurements. We're going to start off by describing the differences between accuracy and precision. These diagrams here are very often used to demonstrate the difference between these terms, and so I'm going to use them. You might find that they are in your textbook. Okay, so each of these diagrams represents a target, and the black marks on the targets represent where we have managed to hit the target. Maybe it's an archery competition, maybe a shooting competition, but this will illustrate the difference between accuracy and precision. What we want is we want to be hitting the center of the target, and in science we want to be getting data that is as close as possible to the true value. So the true value is in the center of the bullseye. We want the data to be very, very tightly packed together so that we know that it's repeatable and reliable, and we want it to be close to the true value. So this first target here is excellent. We have accurate and precise data. In the next example, you can see that we have our type grouping. So we have data that's very precise, it's very repeatable. We know that we're getting data, we're collecting data, and it's all very, very close to one another. There are no anomalous readings, so there's no sort of data points all the way over here, for example. That would be an anomaly. But there is quite a large distance between our grouping and the true value, so it is not an accurate collection of data. In the third diagram, we can see that our grouping is quite poor. The data is spread out over a wide area. It's not very precise. We've got poor repeatability here. If we were to collect more data, we would imagine perhaps that we're going to get data points over here, over here. It's going to be spread quite wide. But one of the things we can do with data like this that is not precise is we can take an average, and you'll notice that the center of this grouping is very, very close to the true value. And so taking lots of data points and then taking an average in this example would be a good way to find the true value. This last one over here is a very poor experiment indeed. It's not precise, it's not accurate. It's not precise because it's very spread out, it's not being very repeatable, and it's not very accurate because the center of that grouping is quite far away from the true value. So that is accuracy and precision, and a talk about repeatability as well. All right, let's have a look at the types of errors that can cause this. So we've got two types of problem. We've got random errors, we've got systematic errors, and they can lead to different things. So random errors tend to reduce our precision, and systematic errors reduce our accuracy. And this is because a random error is something that is not predictable on the day, and you can't necessarily account for it. It might be that you are measuring the weight of something and somebody knocks the table as you're taking a measurement, but nobody notices. It could be that a gust of wind blows through your classroom and gives extra energy to the pendulum that you are swinging and measuring the period of. Those sorts of things. It's not foreseeable necessarily, and it can be all sorts of different reasons depending upon the experiment itself. And what it does is it reduces the precision, and it means that your data is less repeatable. Systematic errors, they reduce your accuracy, and what they do is they move all of your data points away from the true value, usually by the same amount. So we're going to describe some of these on this page here. I'm going to start off with the zero error problem. So if you are using a piece of equipment to take a measurement, you need to make sure that the equipment is calibrated correctly. And usually the way that you would do that, very simply, is to make sure that when you are expecting to see a reading of 0, you are actually getting a reading of 0. So this is the dial of a micrometer. And if you close the micrometer so that you're not measuring a distance, you should experience a 0 measurement. If the distance that you're measuring is 0, you would expect to see 0. If you're using massing scales and you don't have a mass on the scales, you should expect to see a mass of 0 grams. If you're not seeing that, you have a 0 error. This is an example of a micrometer with a 0 error. So if you close the micrometer and the distance that you're measuring is 0, you can see that we don't have that here. We are measuring a distance of, I think that's about 0.2 millimeters. So this would be a 0 error, and it would add 2 millimeters to every single reading that you take. This is a positive 2 millimeters, but it could be a negative value as well. So that would be a 0 error, and it means that your equipment is not correctly calibrated. So you can avoid this by calibrating your equipment before you start. Another can be down to experimental technique, and this here with the meniscus is a very good example of that, and we can also talk about the parallax error. So a meniscus is the curvature of a fluid inside a container, and some you have a concave and some you have a convex meniscus. This one would be an example of water. Water tends to grip the sides of a container and in some cases, if it's narrow enough, pull itself up the tube. This other one here with the convex would be an example of mercury, which behaves in the opposite way. Now, when we're taking reading of the level of a fluid in a container, we want to be taking this dotted line here, so the center of the meniscus. If you are doing that incorrectly, if you are reading this level, for example, or this level, for example, then you are introducing a systematic error into all of your data readings because you are not using the correct experimental technique. Another potentially poor experimental technique would be the parallax error. And that is where you are looking at something from the wrong angle to get the correct reading. When you are taking a measurement where you are comparing the level of one item against a scale, you need to make sure that your eye line is level with both of those things. If your eye line is too high and you're looking down on the object, then the scale and the object that you're comparing it to are going to be slightly offset from your point of view. Same thing if you're too low, you're going to be getting a different reading. So you want to avoid a parallax error because that will introduce a systematic error. If you have, for example, different people taking the readings and one of them goes too high and the other person goes too low, then you're introducing a more random element because you are getting a positive and a negative systematic error being added to your data, and that can lead to a reduction in precision. A quick note about reproducibility. One of the reasons that we record scientific experiments so carefully is to make sure that other scientists can read what we've done and then reproduce our experiment and come to the same conclusions. They won't necessarily collect exactly the same results, but they will be able to see the same patterns. And we need to make sure that we are noting down the equipment that we're using and the exact methods that we're using very carefully indeed, so that our experiment is reproducible. It can be reproduced in another laboratory, maybe on the other side of the world, with similar equipment. All right, let's talk about absolute and percentage errors. Okay, so when we are taking readings, we are very heavily reliant on the accuracy, the resolution of our measuring equipment. You can see two rulers here. This one at the top has centimeters marked, but not millimeters, and this one has the millimeters marked on it. So the one at the bottom has the higher resolution because we are able to resolve more precise measurements. Okay, so let's take some measurements on using these two rulers. We can see that the length of this object here falls between the 5 and the 6 centimetre marks, but we're unable to say anything with any better accuracy than that. So we would write that as saying, well, we know that it lies between these values. So the way that we record that is by saying, okay, well, we're going to say that it's right in the middle, 5.5 centimetres. But it could be as little as 5 or as much as 6. Plus or minus, and then we write down half the resolution of the equipment. So we can resolve 1 centimetre. So our error is half a centimetre. And this means if you add 0.5 or take away 0.5, you're getting that range. Okay. With the second one, this is a lot harder, and I would want to use a magnifying glass on this potentially, but I reckon that falls somewhere between 5.4 and 5.5 centimetres. It is somewhere between those 2 millimetre markings, but I definitely can't say which one it's closer to, but it falls somewhere between the two. So I'm going to write down exactly halfway, 5.45, plus or minus. Now, I can see that the resolution of this ruler is 1 millimetre, so I want to write down half of that, 0.05 centimetres. Okay. Now, if I were to take that away or add that onto this value, it would give me this range, and that's what I'm aiming for. That's what I want. Okay. These are the uncertainties of our measurement. And these, because they have the same units, these are absolute. These are absolute errors or absolute uncertainties. If we were adding or taking away measurements, let's say that we needed to add the length of these two items together, then what we would say is, let's do that in blue, we'd say we add these two values together because we want to combine the lengths. So we would say 5.45 plus 5.5. So those are our lengths. And then we would need to add on the uncertainties because we are using absolute uncertainties. So we would add on the uncertainties that we have. Okay, so with absolute uncertainties, we add the uncertainties on. If you are doing something like calculating an area, and you have the length of one side of the room, and you have the length of the other side of the room, and you are multiplying those values together to get the area, then suddenly the absolute uncertainties are not going to add because we are multiplying the two values together. So what we do in that situation is we turn this absolute into a percentage. So for example, we might have a length of 6 meters plus or minus 5%, and we might have the other length being 7 meters. And we had a better ruler for that one. We were able to measure that to an accuracy of 3%. You can go from a percentage uncertainty and calculate the absolute uncertainty if you need to, in the same way that you can go from an absolute to a percentage if you need to. And that's a fairly simple calculation. You find 5% of 6 meters, and that's your absolute uncertainty. If you want to get a percentage uncertainty from an absolute, then what you do is work out what is this number as a percentage of my measurement. And that would be your percentage uncertainty. When you are multiplying or when you are dividing numbers together, you add the percentages. So for example, with this one, I would have 6 meters times by 7 meters, and that would give me my answer, 42 meters squared. And then we would combine the uncertainties and add them together because we are multiplying, therefore we add the uncertainties, the percentage uncertainties, and this would be plus or minus 8%. Okay, so that's the difference between absolute and percentage uncertainties and how you combine them. All right, last bit. We're going to talk about straight line graphs, gradients, and how to get the uncertainties from these. Okay, so when we collect our data, if you have collected uncertainties for every data point, then you can plot that on the graph in the form of error bars. So an error bar shows you the location of the data point, and then it shows you the uppermost possible value and the lowermost possible value. You can have different lengths for those. It is possible. It depends on the experiment. You may have error bars for all of your data points. They may be different. You can see this one here and this one here. The error bars are vastly different, and that can just be due to the nature of the experiment. It may have been easier to take accurate information at this location compared with that one. Maybe that's down to the design of the experiment or just the nature of the experiment itself. It can vary wildly. Okay, so we have error bars on our graph, and this allows us to take a line of best fit. So on this graph, you can see here we've got our black line, which I'm failing to trace accurately. There we go. There we have our black line showing the line of best fit. That's the straight line that goes the closest through as many data points as possible. So that is the line of best fit. It is as close to possible as to all of the data points, and ideally goes through all of the error bars. The red line has a different gradient, and you can see that that is a terrible fit for this data. It is going through the top of the error bar over here and the bottom of the error bar over there, and it's almost as though somebody has rotated the line of best fit as far as possible to the point whereby it's only just acceptable, and that's kind of correct. The red line represents the line of worst fit. And if you calculate the percentage difference between those two gradients, then you have the percentage uncertainty. Most of these experiments, you take measurements, you plot them against each other, and the gradient will give you your final answer. The gradient might be the value of gravity, or it might be the spring constant for a spring, for example, but it will give you your final answer. And if you need to calculate the percentage uncertainty of that value, then you compare the line of best fit with the line of worst fit, and the percentage difference between those numbers gives you your uncertainty.